Hello, everyone, and welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Jonas Deré from Catholic University of Leuven, Belgium. This is going to talk on simply transitive nil-affine actions of solvable Lie groups.
Okay,
Please.
thank you very much for the introduction. So maybe the title was not the most well chosen. There are non-associative algebras lying behind, but they will appear a bit later after I start with the introduction and the motivation why we study certain structures. So we'll talk about these simply transitive actions, but maybe so that's the motivation, this action of Lie groups, but maybe like sketch the general picture, which might not be too well known for everyone, or maybe it is, and then you just follow it. So a homogeneous space, that's the type of spaces we're interested in, is with one on which we have an action of some Lie group that is transitive. So every point on your manifold looks basically the same. And so actions for me are always smooth maps. So I'm in the manifold case. So and a Lie group acting. So everything is smooth. And so transitive, as I said, means that every point is mapped to any other point by some element. And so every point locally has like the same behavior in your space. And so the question of the talk that we're interested in is like, suppose that our space X is equipped with some additional structure. So for example, it could be a Riemannian manifold. And we assume that these elements, these groups elements, preserve this geometry of the space. And we'll see, I mean, there will be basically only one type of geometry, but this is like the general picture I want to sketch. And suppose that the action preserves this structure, what can we say about the relation between, on the one hand, the geometry, and on the other hand, the algebra of our group? And so in our case, we will make it even simpler. We will assume that our space itself is also a Lie group. And I mean, the action we had was transitive, but it could be like a non-trivial kernel. But in our case, we just assume that the action is simple. And so that if an element is not moved by a group element, then this group element has to be trivial. So in particular, I mean, this action, it's transitive, so you can go from one point to any other point, but you can do it in a unique way. That's our assumption. And so as I mentioned, this is like the general idea of this talk is what can we say about simply transitive actions if we assume additional properties on these maps LG and the left translation. And I will explain what assumptions we want. I will give one classical example, namely we could act on Euclidean space by isometries. And this is already well known, so I would just want to give the type of results we're aiming for. So maybe just as a remark, so if you have this simply transitive action on something that is simply connected, so Rn, then of course the space, your Lie group you started with is also homeomorphic to Rn. And so instead of studying the group on its own, we are basically interested in the Lie algebra. That's just a comment. So many of the results here will be about Lie algebras. And so Milner in 76 already described what Lie algebras have this type of action. And he showed that the Lie algebra splits in a direct sum. And so let me check, they're both commutative. So abelian, and B is just a subalgebra, the U an ideal, and the action of B on U is by skew symmetric matrices. So if you have this decomposition, I'm pretty sure you can cook up an action of isometry. It's basically written already here how you should act on the isometries. And so what Milner showed is that the converse is also true, that you can only have this very naive type of actions on Euclidean space by isometries. And so in particular, we have a strong result about the structure of the Lie algebra. It's two-step solvable and it's unimodular. So not every Lie group can have an action like this. There's a very restrictive class. And so that's what we're aiming for in this talk is we have a certain action on a certain space, and we want to describe what we can say about the algebraic structure of your group acting on your space. And in fact, the next example I will give will almost be already the final thing we're aiming for. We just replace our group of isometries by a bigger group, the affine transformation. So we act with a Lie group, simply transitive by affine transformations on Rn, and we wonder what can we say about the groups G. Well, one thing you can easily see is that, well, this affine group, it's a linear group. You can embed it in GL Rn plus 1. And so a linear group that is simply connected and connected has to be solvable. That's not too hard to show. So there cannot be compact subgroups inside there. And so, yeah, so it has to be solvable. And so from now on, of all the Lie groups, I'm only interested in the ones that are simply connected and solvable. And so that's the picture we have now. And so what Milnor showed in 77 is that if you only want a simple action, so maybe the n is not, I mean, this could be like a bigger dimension than the Lie group G, then you always have a simple action. So if it would not have to be transitive, then it always exists. And in the same paper that he proved this theorem, he wondered like, can I do it for every solvable? Is there like a condition we put on our Lie group by acting on affine space? Or does every solvable, I mean, we already discussed that, it has to be solvable, but is there any other restriction than this, or do all solvable Lie groups act? And so, I mean, Milnor was interested in certain manifolds, affine flat. I will not say too much about it. I'm just here, the Lie group version of it. But so, and there were some positive answers, and I know they predate the question of Milnor, but people were already working on it. And so it was already known to be true if G has a non-singular derivation. So in particular, G is nilpotent already in this case, and Schoenemann showed how you can cook up an action simply transitive in this case. And 2 years later, Schoenemann proved the same result for, I mean, two-step nilpotents always have a non-singular derivation, and so this is a natural extension in some sense to three-step nilpotent Lie algebras, showing that you always have an action like that. And so for many examples that you would cook up on your own, this already, well, nilpotent at least, they already have an action. But there was a counterexample, so more than 15 years later by Yves Benoit, and then later by Dietrich Burde and Fritz Grunewald in 95, to show that even in the nilpotent case, there exist Lie groups that do not have an action like this. So we do not have all the Lie groups, and so it makes sense to study which ones do have and which ones do not have. And maybe some comments. So the original example by Yves Benoit was in dimension 11, so G 11 dimensional acting on R 11 as well. And then Burde and Grunewald generalized this example to dimension 10. Well, it was the same type of example, but so one dimension lower. And they also made it into a family. So there was a parameter inside. And so it's really the lowest possible dimension. In dimension 9, although this is not published, but I talked to Dietrich Burde before, he has a proof, and he's still writing it down, that all Lie groups have a simply transitive action. Okay, and so this is really their family of examples is as small as possible. So we know not all of them, but some of them, and so we can wonder which ones. And maybe it's good at this point to give some example. Well, there's a typo here. This n should be 2. But so suppose you take like a very easy class of Lie groups, R2 semi-direct R, with some one parameter family of matrices. This is a solvable Lie group. It's also sometimes nilpotent, namely if this A is unipotent. And so I listed here 3 types of examples. This is basically the Heisenberg group. I will come back to that one later. This is another solvable Lie group, not nilpotent. And this is the connected component of the identity of the isometries of the plane. And so, but you could say, yeah, this one I can let it act on the plane, but then it will of course not be simply transitive because the rotations have a fixed point in the plane, but you can let it act on three-dimensional space by adding like an extra translation direction for the rotation. So that's, I explained for A3, but you can do it for all 3 examples. You have like an action of this solvable Lie group to affine. Just if you never saw examples of these actions, is good to know. Of course, if A is trivial, like the identity also have the same thing, that's just translation in 3 directions. Okay, I will not say too much about the original motivation of Milnor, but I want to say something because I really like mentioning this conjecture, the Auslander conjecture. So actually Milnor was also interested in like the discrete version of this question. Namely, can you find groups that act properly discontinuous and co-compact? So that's like the corresponding notions for groups, discrete groups. such that you have the same type of action. And so if you have a group like that, then you find a closed manifold as a quotient space. And the question was like, a finely flat manifolds that are closed, can we describe them in a certain way? And so Auslander had a proof of this statement, but obviously it was wrong because now it's phrased as a conjecture. And he believed that if you have an action of this type, then the group has to be virtually solvable. Remember, for Lie groups, we already know this because this group is linear. And so we have this topological, well, maybe topological is not the right word, but we have some argument showing that the group has to be solvable. For groups, it's not so easy. So this is like a big open conjecture in this field of affine geometry, and it's not known whether this fundamental groups or this groups acting have to be virtually solvable. On the other hand, so this is one direction, the easy direction from the Lie groups. The examples of Benoit and then later Bourde and Grunewald also have a lattice that show that the discrete version of the Milnor's question also has a negative answer. So there are discrete groups that do not have this, even nilpotent groups that do not have this properly discontinuous and co-compact action. Maybe good to know, this is also a very famous example, is that so you really need this co-compact. There exist properly discontinuous actions of 3 groups on R3. This is already weird if you think about it. So affine action. I really recommend, if you never read this paper, to have a look at it. It's very geometric, very nice. So maybe this is not the right place to make publicity because this is a non-associative algebra seminar, but okay, it's a very nice paper. And so we know that, yeah, this, you really need this co-compact. And actually the corresponding thing of Milnor's theorem on actions of solvable Lie groups on by isometries was already known by Bieberbach in 1912, just as a small thing. Okay, this was the discrete group version. I will not say anything more about it. I just like to advertise this Auslander conjecture. Okay, so we have this result saying by Benoit and then Bourde and Grunewald that you do not always have an action by affine transformations. However, what I want to say here now is that there is a generalization that we can consider where you do have actions like that. Namely, so if you replace Rn by a different Lie group, then you have more possibilities. And so the idea is the following. Rn is the unique abelian simply connected Lie group of dimension n. And so you can replace abelian by something close to it, namely nilpotent. And I already mentioned the Heisenberg group. So if you take a simply connected nilpotent Lie group, if you are too familiar with it, think about these matrices, upper triangular with one on the diagonal. And so it is one of these semi-direct products of before. And so you can make an affine group for these ones as well. And you can make a similar action of the affine group on H, similarly as you do with the affine group on Rn. And again, these groups are linear. So in particular, if you have these simply transitive actions, they should be solvable. Okay, good. And then just as an example, you can make an action of, this is in this case R3 on affine transformations of the Heisenberg group, which is simply transitive. If you've never seen this before, that's why I give this example. Maybe it's good to know that these actions exist. And so the automorphism that I take, so it's this one on the Heisenberg where you only change something in the center. So you basically add this y with minus t. This t is the parameter of this family of automorphism. And then you get a simply transitive action. It's not too hard to compute this, but just to know that there are actions of, for example, R3 on Heisenberg that are simply transitive. Okay, so what de Kempe showed in 2000 was that if you replace your abelian Lie group by this nilpotent Lie group H, then every solvable Lie group has a simply transitive action. And I will give a new proof of this theorem later in the talk. It's not too hard once you have the right tools. But so for actions on Rn, we have some restrictions. Not every solvable group has one. If we take all possible nilpotent Lie groups, you have all possibilities. But the question I want to discuss today is, Well, what can we say about which Lie groups act on which nilpotent ones? So every G has some H on which it's act, but not every H, because we know that on Rn it doesn't happen always. And so that's the question we're interested in for today. Like, what can we say about the Lie algebras G and H for which we have a simply transitive action? Okay, so that was a bit of motivation why we're interested in the properties I will introduce today. And as you will see, I will go into the classic case now, the abelian. So H being abelian. So the one that I talked most about, the regular affine actions. And now we really will go into the non-associative algebras. So I will have one vector space in my talk on which I will have several different algebraic structures. And so if every time you see a V now, it will be the same real vector space that I will use further on. Okay, and so as you all know, you can make Lie algebras from every associative algebra. I will go to non-associative later, but so what you can do is you can always take the commutator and you make a Lie algebra. And everybody probably already did this a few times in his life. The main point of this why this works is that you can compute the Jacobi identity. You have like a huge formula, everything cancels out and you get 0. And so you have a nice Lie algebra coming from it. But in fact, you don't need associativity to have a Lie algebra. There are weaker conditions that give you a Lie algebra. And one of them that I'm interested in is the notion of a left symmetric algebra. So if you have an algebra that is not necessarily associative, then you have this associator, x, y, in 3 elements, x, y, z, which basically measures how much it's non-associative. And so a left symmetric algebra is one where if you switch x and y, then you get the same values. So x, y, z, the associator of x, y, and z is the same as the associator of y, x, z. Okay, and so in fact, same exercise as before, you can easily show that if you have a left symmetric algebra, then you can make with the commutator a Lie algebra. Okay, slightly more involved, that's true, but I mean, it's not very hard to show that. And so actually what I also like to think about is the other way around. I usually start with the Lie algebra, and if I find a product in this way such that that is left symmetric, and that gives me the original Lie algebra back, then I call this a left symmetric structure on my Lie algebra. So it's the same thing, it's just here I start from the algebra and I go to the Lie algebra. Here I start from the Lie algebra and I go to the algebra, and I give it a slightly different name. Okay, so how is this product related to the Lie algebra? Well, let me write this condition that we had before. So I will write Lx for the left multiplication. And so what we have is that it's left symmetric. And if you write this again, I mean, this is just filling in the formula. And I regroup things. So I just put this one there and this one there. If I look at this equation, what I see here is that the commutator, because that's what I have here, x times y minus y times x, applied to z as left multiplication, gives me the same thing as, so here it's first left multiplication by y and then left multiplication by x minus first left multiplication by x and then left multiplication by y. And so what you see is that there is this map, the left multiplication map, that behaves well for the Lie bracket. Namely, if you take the commutator of the left multiplications, that's the same thing as the left multiplication of the Lie bracket. And so we get a representation of our Lie algebra to the linear transformations of your space V by this left multiplication. So there is this natural map if you just rewrite the conditions from your Lie algebra to some linear transformations. And in fact, we can do more because we were interested in, you're probably wondering, we were interested in these actions. And so we want to say something about the affine transformations. And the Lie algebra there is not just GLV, but is also this vector space associated to it. So we have a semi-direct product, and we already have one relation between these Lie algebra and this algebra here. Namely, we have this map L. But in fact, we can just add some, I mean, G is also defined on the same vector space as V. So that's the same. I mean, I always work on one vector space. I have different structures. And so I can consider the map XLX. I mean, I can consider this element. I can also consider this element. And if I take the Lie bracket and I use the semi-direct product, then what I see here is that in the first component, I just get the Lie bracket on G. And in the second component, because there's a bracket too much here, sorry for that. In the second component, I get this also the left multiplication of this bracket. And so what I see by just a simple computation is that every left symmetric algebra gives me a map from this induced Lie algebra to the affine transformations of V just by mapping X to, so the identity in the first component and this left multiplication map in the second component. So if we think back, I mean, we are interested in these types of maps. If I take the exponential of this map, and I mean, there's a way. I mean, so there's a relation to actions. I can in the cases I'm interested in, I can take this exponential. So this gives me from a left symmetric algebra. This gives me an action that I'm interested in. Okay, and so now, so V is just a vector space. I don't write Rn anymore because I prefer this vector space V, but it's basically what the type of actions we were interested in. And so the two questions that we could ask ourselves now is like, okay, we want to make this action simply transitive. What do I have to impose on my left symmetric algebra so I know that this action is simply transitive? That's one question. And a second question you can ask yourself is, okay, you give me now a very specific construction of actions, possibly simply transitive, but do all of them look like one that comes from a left symmetric algebra? So these are two different types of questions. Like, one, can we guarantee simply transitive? And do we get all of them? And so the answer on both questions is yes. And this is a theorem by Kim in 86. He showed that if you have a simply transitive action, then it really corresponds to a left symmetric structure. And we know the ones that correspond to the simply transitive ones, we call it complete. So there's an extra structure or extra condition we have to put on the left symmetric algebra to guarantee simply transitive. And I will give you the definition of complete. Namely, the definition that Kim gives in his paper is the right multiplication map is nilpotent. That's his original definition. Okay, so this is not the left mode. So we changed the side of the multiplication to have this kind of notion. And so in particular, this right multiplication, it might have different properties, right? It does not automatically satisfy these nice type of properties that I mentioned before here. But okay, this is the one that appears there in this theorem. Okay. Good. So we have a full characterization, maybe some words on the proof by Kim. It's a more geometric proof. So one direction, namely showing that given this this simply transitive action that you get a left symmetric structure, that's really geometric in the sense that, so this simply transitive action gives you a flat torsion-free affine connection on your Lie group G. That's basically equivalent to it. And so what Kim realized is that if you just consider this affine connection, so that maps to vectors, tangent vectors to, I mean, to vector fields maybe, but you can always extend them left invariantly. So if you have two vectors on in your Lie algebra, two elements, you can make the product by just taking this derivative. And then you have these two conditions, torsion free and flat, and basically showed that well, I mean, the first, I didn't really mention I mean, left symmetric was only one condition, but it also had to correspond to the Lie algebra G. And you can check that both conditions really correspond to the conditions to have a left symmetric structure on your Lie algebra G. And the other direction is really completeness, is computing a bit to show that you really have a simply transitive action. I mean, the theorem is not very hard. You can really check it out. It's like 1 or 2 pages, but this gives like a full characterization of left symmetric structures. And Kim uses this theorem to describe all possible simply transitive actions. Well, not on Rn, but up to dimension 4. So I should have mentioned here for n smaller than or equal to 4. So up to dimension 4, he uses this theorem to describe these actions. Okay, and in fact, it's also a bit in this way that the counterexample of Burde and of Benoit and Burde and Grunewald works. I mean, it's a slightly simpler condition is already enough, but okay. So this is like the main theorem for the classic case. It shows you how to go from an algebra from a certain structure to the simply transitive action and vice versa. And this is what I want to emphasize still. This notion of completeness, which I will recall from here, is really the crucial one. So not every left symmetric algebra gives you a simply transitive action, only a certain subclass, and it's characterized by the right multiplication. Okay, good. So the second case I want to discuss is one. Now we focused on the second Lie group that had to be abelian. I will show you how also the first Lie group, by only looking at nilpotent ones, was treated already in full detail. Okay, so the group G being nilpotent, then it was shown that if you have this corresponding morphism on the Lie algebra level, so you split it in two components, the T and the D part, so translation part and the derivation part in a certain way. So this D is a morphism of Lie algebras, but this T is just a linear map of vector spaces, right? I mean, it has a slightly more complicated relation with the Lie algebra. And what Dietrich Burde, de Kimpe, and the Schams showed in 2009 was the following thing. They could characterize the simply transitive actions via these maps T and D. Namely, the T had to be a bijection, so it's a linear map. So it's really an isomorphism of vector spaces, not of Lie algebras, but of vector spaces. And this D had to be nilpotent. So only nilpotent derivations were allowed in that part. Okay, and the proof was not too easy, but to give you some idea, the point was that if the action of G is not unipotent, so if this D would not be nilpotent, then you can always find fixed points for your action. So, and that already guaranteed that somehow this correspondence. And then they had to do some induction argument using the result by Kim to show that if the action is simple, I mean, and you have this condition that you could make it transitive as well. Okay, so there was, I mean, this is really a very short way of describing this proof, but they used this theorem to show, this version of the theorem to show that if the dimensions were up to 5, you could always find some simply transitive action between the nilpotent Lie group. So we both have to be nilpotent in this case. Okay, so we can make this into a new algebraic structure in the following way. So you have, I mean, here you had two different Lie algebras, G and H, and they lived on separate spaces. But of course, if you know that this action is simply transitive, it's a bijection, you can push this Lie bracket on G to the vector space corresponding to H. And so the one corresponding to H, I call it V again. So I have V with this Lie bracket H. I have a second Lie bracket G that I can push to the Lie algebra H using this bijection. So basically I make this T into an isomorphism. I get a new Lie algebra isomorphic to G on the same vector space V. And if I just identify, if I kind of forget that the G was a different one, I find that this map 5 from before, if I mean, basically what I do is I undo this T, I compose with the inverse of T, I get this mapping X to some derivation depending on X. And this is still a morphism of Lie algebras. And so I can write this as I done before with the left symmetric algebras. I can see this as a map Lx going from V to V. I can see this as a left multiplication on my V. And what do I see for the properties of this map? Well, this had to be a derivation. That's what I asked here. So Lx's derivation of H for every X. I have that this map is a morphism of Lie algebras. That's what I had for this D map. I mean, for the composition now. And a third property I have is I still have the semi-direct product. And if I take this into account in the first component, I get that basically the same computation as before with the left symmetric, only I have a second Lie bracket here. It's not just a bracket of X and Y in G, but I have this bracket of H as well. So it's just a computation to show that the fact that this is a morphism corresponds to these properties. And this is the whole idea of the next structure I will introduce, the post-Lie algebra structure, is that instead of coming from these actions, I can just take two Lie brackets on the same vector space, V, I have two brackets, G and H. And a post-Lie algebra structure is basically what I get with this left multiplication. So I just translate the previous three properties to the multiplication. So the first one is this last one here, is saying that, so if I see this as a multiplication, X times Y minus Y times X is the difference of the Lie brackets. That's what I written here now. The second one is saying that, well, maybe the third one is better. The third one is saying that left multiplication is a derivation for H. And the second one shows you that left multiplication is a morphism of Lie algebras. So going from G to the derivations, that's what we say here, of H. Okay, so these conditions are more or less or are equivalent to saying that this map phi of before is a well-defined morphism. So mapping phi of X to X, so is the identity in the first component and some left translation in the second component. And okay, maybe also good to know that if you take H the abelian Lie algebra, so then this last condition somehow disappears. It just says it's a linear map, but okay, we already have that. And so the first one becomes this without the last part. And so you see that you have nothing else than the left symmetric structure. So saying that G is defined as this product and that you have this condition. Well, I didn't really show this left symmetric structure was equivalent to that, but you can easily check that this is the case. So it's like a generalization of left symmetric structures to two types of Lie algebras. Okay, and what's Boerde de Kempe and Verkammen a few years later. So originally they only used this version of the theorem that I mentioned, but a few years later they mentioned, or they realized that they could interpret this result as a result on post-Lie algebra structures. And so they said there is a simply transitive nil-affine action from G on H, if and only if you can find a new Lie algebra on the same vector space as H, because this is an issue you always have. G and H are different Lie groups, so they have different vector spaces for the Lie algebra. And so what you have to do is somehow you find an isomorphic Lie algebra on the same vector space as H, such that this pair that lives on the same vector space admits a post-Lie algebra structure, and again, one that is complete. So, and they needed, of course, now the good definition of completeness. And in fact, we already seen in the previous theorem what complete is, namely, the left multiplication has to be nilpotent. That was what this theorem said. I mean, just reinterpreting this theorem says that the dx, the d's has to be, the derivations has to be nilpotent. And so the derivations were the left multiplications. And so a post-Lie algebra structure is called complete if the left multiplication is nilpotent. So, and in this case, we need that both G and H are nilpotent for this to make sense, to have this theorem. Okay, and so maybe at this point you realize, we have a problem, right? We have two definitions of completeness, one in case that both G and H are nilpotent, and then we talked about the left multiplication, and one for left symmetric algebras, which was with G solvable and H abelian, where the right multiplications play the role. And so there is some overlap, namely if G is nilpotent and H is abelian, but, and this predates the previous result already, Siegel showed that if G is nilpotent and you have a left symmetric structure, so the intersection of both definitions, then in fact these definitions are equivalent. Namely, the left multiplications are nilpotent if and only if the right multiplications are nilpotent. So that's a good thing. We have two different definitions of completeness, but they correspond on the intersection. But already shows that, so the definition of completeness usually comes from these simply transitive actions, and they just say, oh, the definition we have is the one that corresponds with simply transitive. and we call that one complete. And then there's always a non-trivial, I mean, this is not a very easy result. It's kind of some computations to be done. So it's always a task to show that the both definitions correspond. Okay, good. So that's where I started working on this problem. So the question was, what can we say if G is solvable but not nilpotent, and H is nilpotent but not abelian? That's like the case that is still open. We have two special cases that are fully understood. And in fact, we had, so we want to show somehow when there exists a simply transitive action. And so we have this morphism. We would like to say, given the morphism, we want to see whether the action is simply transitive. That's one thing we want to understand somehow. If I give you an action on the level of the Lie algebra, you want to say, this one is simply transitive, this one is not. And the second question that you might have is that if I give you just two Lie algebras, one is solvable and the other is nilpotent, you would like to determine yes or no whether there exists a simply transitive action. And of course, you could say, well, if question one is answered, I have an answer for question two by iterating over all possible morphisms. Okay, this is maybe non-trivial to iterate over all these morphisms. So maybe it's good if we have a different way to see the second question. And so I will try to sketch in the next 20 minutes the answer that with my co-author we had on both questions. Well, the first one is maybe not yet very much finished, but let me show you where we're at. Okay, let me first focus on the general case, on something similar as what we've done before with the left symmetric and the post-Lie algebra structures. What I showed with my co-author, Marcos Origlia, last year is that if you have a simply transitive action, then you always have a post-Lie algebra structure on a pair where you always have to do this trick where you put them on the same vector space. So where you have a new Lie algebra isomorphic to the original one. And okay, it's maybe good we didn't realize we used different techniques, but there is in fact also an independent and more general theorem by Bai, Guo, Sheng, and Tang that uses post groups, and they also come up with this relation that if you have some simply transitive action, that you always have a post-Lie algebra structure. Okay, but again, I mean, this is not the main result maybe of our paper, but we show that given a simply transitive action, you have a post-Lie algebraic structure, but then you always have this question like, how can I see with this post-Lie algebra structure whether there is a simply transitive action corresponding to it? And we show that this holds if and only if the corresponding the post-Lie algebra structure is complete. So maybe it was somewhere on the slides with plus means post-Lie algebra structure. I just like to abbreviate that. And so again, I mean, this is the same type of result as the previous one, but the question is then always like, what is completeness, right? You can write this statement, but you have to define completeness. And what our version of completeness is that, so, okay, this maybe, that's an important condition. This is only for two-step nilpotent, H two-step nilpotent. So it's no longer abelian, it's the next step, but we don't have it in full generality. And so if H is two-step nilpotent, then we call the post-Lie algebra structure complete if the right multiplication minus 1/2 the adjoint of H, because I have two Lie algebras, I have to specify which one. So 1/2 the adjoint of H is nilpotent for every Y in my vector space. And so we not only showed that we needed this correction term, that it works with that one, but also that it is necessary. So we have examples where if you just look at the right multiplication, like in Kim's result, it's not enough. So you really need this extra term. And we also have three-step nilpotent examples. So H three-step nilpotent, where this statement does not hold. So we have a notion of completeness that works in two-step nilpotent Lie algebras, but we don't, I mean, we have some ideas on how to continue, but I mean, for sure, this is not the right notion of completeness for general Lie algebras. Okay, and actually the proof is very nice, and maybe I want to share a bit the idea of it. So if you have a two-step nilpotent Lie algebra H, you can make a map from the affine transformations on H to the affine transformations on the underlying vector space. So basically what I mean here is that I forget that this is a two-step nilpotent Lie algebra. I make it abelian. And that's the affine space there. So it's V semi-direct GLV. And what I do is I just map an element X and a derivation D. I map it to the same element X, and D plus 1/2 the adjoint. I already see 1/2 the adjoint appearing. And I mean, it's really an exercise basically to show that this is an injective morphism of the algebras. And so I mentioned that post-Lie algebra structures, they can be seen as this, I mean, there's this way of seeing it as certain subalgebras, or where you have identity and then some derivation part. Well, I've written it here in full detail, so you can change your post-Lie algebra structure between G and H into a left symmetric structure on G by changing the left multiplication, namely you add this term, right? So it's the same. I mean, these are two sides of the same medal, so you can change your post-Lie algebra to a left symmetric by adding 1/2 the adjoint. Okay, and so what we showed in our work is that this map, this changing a post-Lie algebra structure to a left symmetric one, preserves simply transitive action. So if your original action is simply transitive, then the corresponding action of the left symmetric one is also simply transitive, and vice versa. And so because we have the result by Kim that says that the right multiplication corresponding to this one should be nilpotent, so that's an if and only if condition. Well, basically we have that this guy should be nilpotent, and this is written for left multiplications, but if you make it in the right multiplication version, then you get our notion of completeness. So that's, in a nutshell, the idea of the proof is that we push our action from something two-step nilpotent to something abelian to make it work. So it's, I mean, the argument is very easy to follow and to see. And so something we also had to show was that using this map, we can show that both definitions of completeness correspond, because we had two different notions, right? We have now the Burde de Kimpe Verkammen version, which says the life multiplication. If G is nilpotent and H is two-step nilpotent, we have their version of completeness. We have our version of completeness with the extra term here. And in fact, both of them are equivalent. That's like always a step you have to set, because they are somehow always getting more complicated definitions of completeness. Okay, so that's a bit how far we got with this first question. So if I give you an action, or I give you a post-Lie algebra structure, I can determine in the two-step nilpotent case whether it's nilpotent or simply transitive or not. Namely, what you have to check is you compute this guy. I mean, it gives you a matrix with some parameters, and you compute whether it's nilpotent. So you just take it to the power of the dimension of your vector space, and you have like a yes or no answer to your question. It's easy to implement it in computer software, saying like, yes, your action is simply transitive, or no, it is not. Okay, and so the question, I didn't write it down here, we're working on is like generalize this to higher nilpotency class. Okay, but then there's the second question, because I mean, with this definition of completeness and the extra term, I don't think it's always very easy to show, if you give me two Lie algebras, to show yes or no there exists a simply transitive action. And actually in previous work, we give a better way to show this. I mean, this is ideal. If I give you the action, you say yes or no, it's simply transitive. But if I just give you the Lie algebras, you have to do this for all possible maps. So all possible post-Lie algebra structures, and that's not always too easy to see. And so this is what the next section is about showing existence of a simply transitive action using the semi-simple splitting. So what is the semi-simple splitting? So if you start with the solvable Lie algebra, you can take its nil radical. So it's all the elements where the adjoint is nilpotent. And then you find this short exact sequence, nil radical, solvable guy, something abelian, 0. And so in the easiest case, you have the short exact sequence, the splits. That's the easiest type of solvable Lie algebras you can make, namely nil radical semi-direct T, and T is an abelian subalgebra. But of course, not every solvable Lie algebra is split. And so the idea of a semi-simple splitting is we put it in a slightly bigger Lie algebra that is split. And I'll just, I mean, I've written down the definition here. But maybe if you never saw this is a bit too much. So the ideas of a semi-simple splitting is that you embed it into a bigger Lie algebra G prime, which is the semi-direct product. It is an action by semi-simple derivations. Somehow the last two conditions are saying that the G prime is minimal in this way. So the intersection, I mean, there should not be an intersection with the T and G. And I mean, it's a bit technical, but basically this is also to make it unique and to make it like the smallest possible in certain way. Okay, so let me just give two examples to show what's going on. Of course, if you start with something nilpotent, you don't have to do anything. Then it already splits with like a trivial action. And suppose that's maybe an easy example. You have a semi-direct product, like some nilpotent guy and some extension of dimension 1 with some derivation. So if this D would be a nilpotent derivation, of course, then your whole Lie algebra is nilpotent and you're in this first case. If it's not nilpotent, you can split it into its semi-simple part and its nilpotent part. And what is the semi-simple splitting? It's basically, well, this should be an N, not an U. So the nilpotent, an S, I mean, not a U. So you split it in a semi-simple part and its nilpotent part. You add like an extra dimension. And so you embed your Lie algebra in there. And so basically what you do is this nilpotent guy, you add it with the nil radical of G prime, and then the semi-simple part is what goes into the T part. Okay, just as in a nutshell, what the semi-simple splitting does in this kind of example. And there's a general type of construction, and maybe I don't have too much time to explain everything, but so there's a similar way as I did here. You take the adjoint representation of G into its derivations. Again, because it's solvable, you get that this image, you get semi-simple part. This will be an abelian subalgebra. And then, you can do the same type of splitting as I done before. Okay. Yeah, I see there's a question. Yeah, I think this is a very old notion. I'm not claiming this is a very new thing. I'm not sure if Maltsev, probably Maltsev came up with this. I'm not too sure where it originates, but I'm not. I always read the name the semi-simple splitting, but it could be called Maltsev splitting as well. I'm not too sure, but it's a very classical notion in Lie algebra. So this is all not new. I just needed it to show this existence of simply transitive actions. So I will look, maybe it's good if I look into it and see if it's called Maltsev splitting as well. Okay, good. So the nilpotent, the nil radical I get here, I call it the nil shadow. So that's just an easy way. It's like the nilpotent Lie algebra resembling my solvable one the most. Okay, and so what I showed with, this should be 2021, it's already published. We showed that using this semi-simple splitting, or Maltsev splitting, probably it's the same thing, you can check whether you have a simply transitive action. So I give you the two Lie algebras, G and H. You've computed the semi-simple splitting of G, and you try to embed it in the affine transformation, but in a very specific way. Namely, the N, the nil radical, this nil shadow, should only consist of nilpotent elements. And I will explain below what it means. The T should be only semi-simple elements, and the map T, which is this, the same as in the Burde, the Kimpe, the Schams theorem, the translation part, so the non-derivation part on this nil shadow should be a bijection. And so if this simply transitive action exists, we can even embed this T part as a subalgebra of the derivations. And I know this maybe looks complicated, but I will give examples to show how you can compute these things. But so maybe first about this nilpotent and semi-simple. I already mentioned that this affine transformations, they are linear. So on the Lie algebra level, it means you can embed it as a subalgebra of GLMR. And so there you have like this decomposition in semi-simple and nilpotent part. And so you just call something nilpotent if it doesn't have a semi-simple part, and vice versa. So there's a good way of defining these kinds of notions. Okay, but I will show like in low dimensions how you can check for examples what is going on. So let's start with dimension 3. So I already said the actions of nilpotent guys on Rn or up to dimension 4 were treated by Kim. So this is like the first new situation that you can make by acting on some nilpotent H. And I mean, I just list here all the Lie algebras, solvable ones in dimension 3. So you have, okay, you also have the abelian one, of course, I did not write it down. The Heisenberg one is the only nilpotent one, and you have those three, about one here, and then two families here. Okay, and so we wonder like which one of those acts on the only thing that it makes sense, namely the Heisenberg one. So we always act on a nilpotent one, and so this is the only non-abelian nilpotent one you have. Okay, and what we showed using this construction is that it can only act on the Heisenberg one if you either have this one, you have the third one, but then with parameter plus or minus 1, or you have the fourth one with parameter 0. So there's like, of all possibilities, only a very limited ones that can have a simply transitive action. And the way we do it is as I described. So you always start with your Lie algebra and you compute of the guys that act, these are the G's here, the semi-simple splitting. So for the first one, what you do, and I did it here in full, so you have the adjoint map here of E1. So you split it into its semi-simple and nilpotent part, and then you do, I mean, a bit the trick as we did, I mean, I explained before, you get this guy. So this part, gives you, I mean, the Heisenberg one, this nilpotent part, and the semi-simple part is then one that acts with 1, 1, and of course on the nilpotent guy that you, I mean, these two commute, so it acts as 0 on the third vector, and so you have eigenvalues 0, 1, and 1. So the 2 ones coming from here and the 0 from the action on the nilpotent guy. Okay, good. So you have the semi-simple splitting, and you can wonder, can I find an action now? And what you see is that here, well, first I did it for the other two guys as well. You compute the semi-simple splitting, and here you have R3, semi-direct R, so you don't have a nilpotent guy, and these are the ones you get. And you see the eigenvalues of the derivation are 0, 1 lambda for this guy, and 0 lambda plus I, lambda minus I for this one. So it's just a computation. You compute the semi-simple splitting, it's something you can do. Then you want to embed the semi-simple part, this T part. So what we showed, and it's a very nice lemma to do, is that the eigenvalues of this T part correspond to the eigenvalues. So let me explain what is going on here so the T acts in two different ways, right? It acts semi-directly on the nil radical. That's the adjoint that I write here. That's in your semi-simple splitting. These are the eigenvalues that I've written here. So 0, 1, 1, and these guys. These are the ones that I've written here on the right. The S is really after the embedding, so it's derivations of H. And it's yeah, so it's as derivations of H, it's after the embedding. And so these are two different sets of eigenvalues, and in fact what we showed is that they have to be the same. So if you want to embed your T as derivations of H, you already know its eigenvalues, we computed them. And so the eigenvalues of a derivation on H3 semi-simple, they're always of this form A, B, and A plus B. So A and B could be complex, but then on the center they have to be real. And so if you check my possibilities here, so 0, 1, 1, I can do that. 0 plus 1 is 1. You get a derivation of your Heisenberg. But here, if I want that 0 plus 1 is lambda, then lambda has to be 1. You can find other combinations, right? You can do 1 plus lambda has to be 0, then lambda has to be minus 1. So I have two possibilities, 1 and minus 1. And if I do 1 plus lambda, no, that's the one I already did. If I do 0 plus lambda has to be 1, I also find that lambda has to be 1. So there are only two possibilities, plus or minus 1. And here it's even more restrictive. So the only complex ones that I am allowed to have are the ones that sum to my A plus B. And so if I sum those two, I get 2 lambda, which should be 0. And so it means that lambda has to be 0. And you see that I find these conditions plus or minus 1 or 0 for my action. So already embedding this semi-simple part gives me the conditions that I need. And then the only thing we have to do is show that the actions exist. And to find this, I mean, you can embed the nil shadow. We already know how we should embed the t. That's already difficult. And then it's always very clear how we have to add the n. So we have to make this such that this translation part was a bijection. But in fact, I mean, it's very easy to do. So for the Lie algebra, this one, I mean, this was of this form H3 semi-direct R. You can just embed it in the natural way because this is H3. You just embed the nil shadow as the identity. And in fact, this works in general. So you can always embed, if this guy I mean, this nil shadow, you can always let it act on its nil shadow. And I mentioned in the beginning that I would find or give a new proof of this result by the Kimpe that says that you have a simply transitive action on some h. Well, this gives you this result. And so that's what I mentioned here. And then I mentioned, so for the 3 examples, you have to give the embeddings, and I just wrote them down here. It's not too hard. And so we did the same thing in dimension 4. You have some, I mean, 2 possible nilpotent guys. This is the abelian guy. And we did the same thing. And I mean, if you check the paper, I mean, it looks very complicated, but once you have this semi-simple splitting, it's very easy to find this thing. So that's an answer to the second question, like, if I give you G and H, these are my G's, these are my H's, it's very easy to check whether there is a simply transitive action using this method with the semi-simple splitting. Okay, so I hope that I introduced you a little bit in the world of these, why we care about complete post-Lie algebra structures, and if there are any questions, I would be happy to answer them.
Thank you very much. Yes, indeed. Whether there are questions. There were some comments in the chat.
Yes, I saw that they will mention that semi-simple splitting, that it's also called the Maltsev splitting. I mean, so there's a reference now, so it seems to be correct. So I found it in the work of Siegel. It's called semi-simple splitting, so that's the word I note. I didn't want to. Yeah, I mean, it's a well-known notion in this solvable world. I was not aware of the Maltsev name.
Maybe there are some other questions. Okay, so I guess there are no questions. Thank you very much for your nice talk. And
okay, with pleasure.
So it was, yes. So, and I would also like to thank all the participants of this session, and wish you all a nice week. So I guess
Thank you.
can stop.